Okay, so today I'm going to talk about deep learning-based recommendation models with site information. My group has been working on recommender systems with the site information since about 10 years ago. We started with recommender systems by leveraging social networks, and then also review users' textual review information, as well as item categories. So here's the agenda for my talk. First, I will give a brief introduction of a recommender system and highlight the two important issues, data sparsity and code start. And the site information can be leveraged to cope with these two issues. I will talk about I will categorize the site information into based on their representations, and then I will talk about focus on the deep learning based models with by leveraging those different kinds of site information, and finally I will point out some future directions in this sub area of recommender systems. So nowadays we're facing this issue of information overload. So what is information overload? I believe everybody knows, and basically we're facing too many options. And then, for example, in a grocery store, there are different kinds of products, different kinds of brands, different categories, and which one we should choose. And also for movies, there are different kinds of movies, and the new movies come out every year, and which ones we should choose, right? Choose to watch. So when we have too many options, it's also a not good thing, right? We have to choose some options. So this is a very headache problem, and this problem can be solved by recommender systems, because recommender systems can model users, model their preferences, their interest, and then can provide personalized recommendation based on these user models and user profiles. And so that's why recommender systems has become a very popular topic in academia, as well as industrial domain, industrial as well. It is widely applied in various application domains like e-commerce, right? This is actually popularly this is the domain where the recommender systems has been popularly applied, and also the travel business, the point of interest, and also social networks as well, and many other multimedia websites. So it okay. The light is automatically off. Yeah, so basically the recommender systems is getting very popular nowadays, and that's why we have to study it. So most of those recommender systems are based on collaborative filtering. The basic idea is that if we want to provide a recommendation to a user, like this one here, and then what we can do is that we can find those similar users, and then to check what the product item bought by this similar user, and then this product can be this item can be recommended to this user. So this is the basic idea of collaborative filtering. But then for this collaborative filtering approach, there are two common problems, issues, and one is data sparsity. Because as mentioned earlier, there are just so many options, so many items, and even those most active users, right, only rate a small set of items. So this is a data sparsity issue. Another issue is the cold start. So for the cold start items, there is very little chance to receive ratings, and for the cold start users, they don't have any ratings. So it will be very hard to learn their preference. So these two issues, and we have to resolve these issues. When we resolve those issues, then the accuracy of recommender systems can be much improved. And the site information can be leveraged to cope with those two issues. By site information, what I mean is that the kind of information that other than those ratings, the information could be social network, could be item categories, could be some other other type of information, which I will talk about later, the categorization of site information. But here, I give you a toy example to show how site information can help with the recommendation. So let's suppose this user Alice actually is a code user. And if we just rely on the ratings, and then it will be very hard to provide accurate recommendation for this user. But luckily, we know the social network of this user, Alice. And then we know the friends like Cindy. And also for Cindy, Cindy is not the code user. We know that the Cindy likes these movies. And then because Cindy is a friend of Alice, then we can recommend those movies to Alice. Because we based on the assumption that the friends will share a similar interest. And also for Bob, and Bob has watched these kind of movies, this set of movies. And then because this set of movies, and then the second set of movies, both are cartoon movies, and they belong to the same category. So then this second set of movies can also be recommended to Bob. Okay, so this is just a toy example to show how different site information can help. And if we want to do a categorization of site information, there are just too many different kinds of site information. So in here, I want to just categorize them based on the different representations. So there are basically two different categories, two big categories. One is structured, another is unstructured. For structured site information, there could be flat features. I will give you an example in the next slide, and also feature hierarchies, the hierarchy of the feature, and also the network features. Basically, the features are formed in the network, and also knowledge graph. I will talk about knowledge graph as well. And then another big category is non-structured, like texture features, images, and videos. All these this set of site information are non-structured. Okay, unstructured. For flat features, here is just one example here. The flat features could be like the categories of movies and the music. And the reason we call it flat features is because these features are in a flat format, and then they are basically independent from each other. But comparably for the feature hierarchy, and it's actually to those features, those site information form hierarchy. And this hierarchy actually has some relationships in this hierarchy, there are some relationships between different, for example, the categories. This lower layer categories are affiliated to the high layer categories, and then within the same high level category, right? Like for example, the fashion clothes, and these categories all belong to the both affiliated to the fashion category. So there's some relationships between different categories in this hierarchy. It's different from the flat representation, because in flat representation, we do not consider the relationships between different, for example, the categories. For the feature hierarchy, what we can, the typical difference with the flat feature is that we can make use of these relationships between categories in the hierarchy to provide more fine-grained recommendations, more accurate recommendations. For example, if we know that, for example, we know a user bought skirts, right? And then likely she will likely also bought heels because both under the fashion clothing category, instead of buying athletic shoes, right? So because this kind of shows is actually from a different bigger category, high level category. So this hierarchy actually gives us more information. And another network features, and the typical example is a social network, where the users form a network, form a social network, and it's like a graph. But this kind of graph is a homogeneous graph, because there's just, in this graph, there are just users, and then the links between users are the friendship relationship. And so it's there's only just one type of a link, so it's homogeneous. But then we also could have a knowledge graph to integrate all kinds of different side information into this graph. And this graph is a heterogeneous graph. And there's different types of nodes, as well as different types of links. So this is a heterogeneous graph. And sometimes we call it the heterogeneous information graph, HIG. HIG. So, or some of the researchers call them, some of the papers call it knowledge graph. So these are the structured side information. And for the non-structured side information, there could be text, could be image, could be videos. And for example, the text could be like textual reviews provided by users, because the platforms like TripAdvisor allow users to provide detailed textual reviews about, for example, the hotel. And then in this textual review, it provides more details about the different aspects of the hotel and about the services. And the images, there could be images about the hotels, like about the hotel room. And also there could be videos as well. And these are non-structured side information, and it could be also leveraged to couple with the data sparsity and the cold start problem. And if we are talking about those fundamental methodologies for leveraging side information, it actually evolves from with the different stages. In the early stage, it was mostly memory-based models. Could be either user-oriented or item-oriented. User-oriented will find the similar users. Item-oriented find the similar items. And then this memory-based models evolved to the latent factor models. And those latent factor models will just try to categorize users and items by a number of latent features. And for example, this probabilistic metric factorization, collaborative metric factorization, and factorization machine, and these kind of methods. And then afterwards, they evolved to the representation learning models. And compared to the latent factor models, right, the representation learning models are actually more effective for recommendation, and because they can capture those local item relationships by using the item embedding technique. And then more recently, we know that the methods we evolved to the deep learning models, and the deep learning models are more powerful and can give us more accurate recommendation results. And these approaches can learn nonlinear latent representations and through various types of activation functions. So, for example, this multiple MLP and the CNN and RN, I will talk about those in a few slides, in the next slides. So in the next few slides, I will first talk about those basic, briefly talk about those basic deep learning models, and then just give high-level ideas of those different types of deep learning models. And then I will talk about how those models, and mostly give you some examples how those models can leverage the different types of different representations of side information. And then I will give you some some highlights, some interesting findings, and also conclusions. So one basic deep learning model we're familiar with is this autoencoder based model. It's just the simplest neural network with the 3 layers, right? You can see the 3 layers, and then the high dimensional input layer will be projected into the lower dimensional hidden layer, and then finally decoded to the decode the hidden layer to the output layer. And this basic model, this autoencoder is quite flexible, can be extended to fuse both structured and non-structured side information by learning those contextual representation of items from those flat features. Later on, I will give you example of that. Another deep learning model is this multi-layer perception-based model, MLP, and which is also widely used these days in recommender systems. And it has one or more hidden layers with the arbitrary activation functions that can provide levels of abstractions, and it can efficiently extract high-level user and item representations. And this model is also flexible, can easily fuse those structured side information by concatenate the flat features with those user or items as input data. So I will give you example later on as well. And one example of this MLP-based model is this deep matrix factorization model. And this model is just utilize the multi-layer nonlinear projection to learn the user and item representation by making use of both implicit and explicit feedbacks. And it's actually published in this paper. There are also other 2 examples of this MLP-based model. These 2 models are the neural collaborative filtering and the neural metric factorization, and these 2 models are proposed by this same group, He and others. And this model basically try to integrate the general metric factorization with the MLP, okay? And then the general metric factorization will apply a linear kernel to model the user item interaction in the latent space, and then the MLP will use the nonlinear kernel to learn the user item interaction function from the data. And then both this GMF, the general metric federation, and MLP will be integrated, concatenated, and fed into this neural MF layer. So this is just the high-level idea of these 2 models. And another deep learning model is this CAN-based model, the convolutional neural network. And for example, this NCF, showing this figure. And this is proposed by He and others as well. And this model first utilized outer product, which is this interaction map to explicitly model the pairwise correlation between user and item embeddings, and then employ this CAN to learn the high order correlation between the embeddings from in the hierarchical way. And this CAN-based method, right? It has convolutional layers and polling layers and also fully connected layers. And it actually consider the input data as an image, and then use this capture the local features. So the nice thing about this CAN-based method is that it is capable of modeling this non-structured information, like text and texture information or image, and then you can capture the spatial patterns and the local relations between features in the image. So this is the nice thing about the CNN-based method. And also another method is RNN-based method, the recurrent neural network. And this recurrent neural network has been introduced for those mainly for the temporal recommendation and sequential recommendation. For example, the next item recommendation. For example, this is this model, which is STRNN. This is the proposed for the next location recommendation, and it has this models both the temporal and the spatial context in each of the layers, and with the time specific as well as distance specific transition metrics. So the nice thing about this RNN-based method is that it is able to memorize those historical information and find the patterns across time, and able to learn the long distance dependencies with arbitrary input and output lengths. So it's this kind of RNN-based methods is more suitable for those sequential recommendations, and also can generate text for those explainable recommendations. So this is the benefit, the advantage of RNN-based method. The final deep learning model I want to just briefly mention here is this attention-based method. So the idea of attention-based attention mechanism is that it comes from those computer vision domain. Basically the human's visual attention focuses on certain part of the image. So you can actually, the attention-based methods can distinguish the different importance of the input data. So for example, this model is called ATT-RECT. It is proposed to leverage model both the short-term interest and the long-term interest of the user, and to provide a sequence-based, sequence-aware recommendation. So now I want to just give you some examples of deep learning-based models that leverage those different representations of features. I will start with the flat features. So this, I mentioned earlier, this autoencoder is the simplest deep learning model. And this autoencoder is feasible to, flexible to fuse these flat features. It can make use of both ratings and side information. The side information here is in the format of flat features, in the flat format, like those item categories and the user gender. And it basically makes use of two additional stacked denoising autoencoders with the side information as input. And then these will be trained with the metric factorization. So this is the autoencoder with the flat features. And MLP model can also be used to leverage flat features. It will, for example, this wide and deep learning model proposed by Chen and others. And this model will jointly train the wide linear regression model and the deep neural work. The categorical features, is the categories of the categories. The categorical features are basically in the flat format, and they are converted into this low dimensional embeddings, and then fed into the hidden layers of the deep neural network. So this is the MLP-based model to leverage the flat features. So basically, to summarize the different, among those deep learning models with the flat features are typically leveraged by 3 different ways. The simplest way is this pre-filtering. The flat features will be used to pre-select some items. If, for example, if the items are from the similar or same categories, they are positive items, and then if the items are from different categories, then there are negative items. So this is the pre-filtering approach. And another type of approach is also straightforward approach, which is the concatenation approach. Then in these deep learning models, you will just concatenate all the feature factors together and fit them into the proposed network's architecture. And the most fine-grained approach is this projection approach. So it will employ this neural network to learn the user and item representations on the different context. Okay, basically either user or item contextual representations. So projection is the most fine-grained approach among those different deep learning models, the different ways of leveraging flat features by deep learning models. So now I move on to the models that leverage the feature hierarchies. So here I just give an example of this 3D convolutional network, and this network combines section clicks and the content features. Like content features are those category hierarchies into this three-dimensional CNN, okay, three-dimensional CNN, and then with the character level encoding of all the input data. And then these three-dimensional CN will concatenate the current. What this does is that it will concatenate the current category along the path, okay, along the hierarchy, all the way to the root, okay, with all the ancestors of the current category, and then use this sequence of the category features, and then to concatenate all of that, and then utilize that information in the hierarchy. Okay, so this is the way to utilize the information in this feature hierarchy. So there's several advantages of feature hierarchy. So I mentioned earlier when we compare the feature hierarchy with the flat feature, right? The feature hierarchy actually has some embeds some relationships between those features. And also when we leverage feature hierarchies by deep learning models, there are several advantages. One is that in fact, in many of those applications, like for example, Amazon website, there's feature category hierarchies provided by domain experts. So the feature hierarchies are actually widely available. So it's easy to obtain. And also the feature hierarchies provide rich information and can be used to, if we leverage this feature hierarchy in the correct way, then we can often get more accurate and also sometimes diverse recommendation results. And another thing is that the feature hierarchy, right? It's actually not very heavy, and it's quite lightweighted, and so it can when deep learning models that leverage those feature hierarchies, actually it turns out that the computational cost of those deep learning models will not be that high. So it's quite efficient. So it actually has this very good, these several advantages if you leverage feature hierarchies in the deep learning models. So then I move to the network feature. So mostly the social networks, and there's a lot in the literature. There's a lot of work on actually quite recently. We see that there's quite a few deep learning models try to leverage network features, leverage the social networks, and about maybe 2 years ago, getting very popular. But before that was mostly just those MEF-based approach. And so here I give you an example of this CN-based approach to leverage network features. It will extract the latent deep structure feature representations by considering this input network, the social network, as an image. And then the user's embedding will be influenced by their friends' embedding. And so this is basically the idea. So this is just one example. Another example is to use the MLP-based approach to models to leverage the network feature. So here, what this model does is to first use this node-to-vec to learn the embeddings of all users in the social network, and then take the average of the embeddings and then find the k most similar neighbors for each user as the input of the MLP architecture. And so then this MLP architecture will learn the nonlinear features of each user from the social relations. So this is the MLP-based method. There are some interesting findings among when we study these different deep learning models with network features. One is that similar to those flat features based approach, and then the network features, when we make use of them in the deep learning models, it actually also evolved from those simple pre-filtering approach. Remember this 3 different types of approaches of leveraging the flat features, right? There's pre-filtering, and then the moderate summation will through this SVD feature, and then finally the deep projection. So all the deep learning models with network features can also be categorized in these 3 different ways. And also, we, based on our experiments and also the studies by the papers in the literature, we find out that the deep learning models can increase the performance compared to those latent factor models. When, as I mentioned earlier, the network features are mostly leveraged by those latent factor models. Only recently we see many of those deep learning models that leverage the network features, but we can clearly see that the deep learning models can do better job. Okay. And also, what we find out is that because the network features, right, we can consider as a graph, it's a homogeneous graph, right? Then we can actually leverage those graph based deep learning models like graph convolutional networks like GCN and graph neural network GN, all these kind of advanced graph-based deep learning models to better utilize the network features. And another thing is that there's, as I mentioned, this deep learning models to leverage network features is just in the early stage. Recently, I was senior PC for the III conference. I see also several papers about that, but it's still in the early stage compared to the long history of latent factor models that leverage network features. So there are many of those interesting ideas that already utilized in the latent factor models with network features haven't been utilized in the deep learning models. I feel that there's a lot of room for us to do to propose some new deep learning-based models to better leverage new network features. For example, we can make use of the distrust information. We can also consider the trust propagation, and all these haven't been proposed yet. And then for the knowledge graph, there are basically 2 types of ways to leverage knowledge graph in deep learning models. One is this graph embedding based method. And these methods will use the conventional graph embedding methods like trans-E, trans-R, and we're very familiar with. Another type of approach is called methods is the path embedding based approach. Basically, you will extract the connected paths in this knowledge graph, and then try to encode those paths with using the deep learning models. And for example, the map paths, we heard this map paths before, and then this path will be encoded by the deep learning models. And the more advanced approach is this propagation-based methods. Then these methods will take advantage of those graph embedding-based methods, as I mentioned for the network features like GNN, GCN, and instead of we directly extract the paths in a knowledge graph. And then this propagation is basically a kind of automatic way to get the path information. And then this is the end-to-end approach. So here I just want to among all those deep learning-based models with the knowledge graphs, I will just briefly mention this example. This is an approach proposed by my former PhD student Shen. This approach first extract those paths between users and items, and then will use the batch of IN. So it's not just a single IN. So each IN will be used to will be corresponding to one path, and then this batch of IN will be used to learn the path influences on the user item interactions. So this is the approach proposed published at RecSys 2018. So there are some conclusions from all the deep learning models with knowledge graph. So first of all, again, this is not surprising, and the deep learning models with knowledge graph can perform much better than those latent factor models in terms of accuracy, but then it is actually in the cost of the computational power, the efficiency and the scalability. So because deep learning models tend to have a high computational cost and have a limited scalability. And also propagation-based method will be better than the other two types of methods. This is understandable. And also the most of these existing methods will rely on those conventional knowledge graph embedding or graph embedding methods like trans-E and trans-R. But there's very few of those methods try to employ this GCN and GNN to further boost the quality of the recommendation. So I think there's still room for us to do. But then of course we understand that the GCN and GNN, they are quite heavy approaches, heavy models. And another thing is that knowledge graph is different from those network features. It's actually heterogeneous graph, and it has different types of nodes and different types of links. Basically, the node between the nodes, the relations have different types. So how we can better utilize those heterogeneity to deliver more accurate results. This is still an open question, direction. Okay, so very briefly talk about texture, how the deep learning models will leverage the texture features. Here I give you an example of this multitask learning model. Basically, this model extends the MEF approach by using the texture features extracted from reviews. And these will serve as the regularizers for the user and item embeddings. Then the embeddings of each word in the relevant review is sequentially fed into the relevant review, fed into this bidirectional GRU, gated recurrent unit, to learn the textual features for the users and items. It's just one example. So the texture feature can be leveraged into two stages. One is the early stage and one is the later stage. For the early stage, it's basically what it does is to concatenate the text embedding in the word level with the user embedding or item embedding. So this is the early stage. Or in the later stage, you can have you can have two parallel models. One is texture model, text module, another is the rating module, and then use the texture module to regularize the rating module, which is actually the previous example that the example that I gave in the previous slide. But there's from all these models, what we conclude is that we can still leverage those advanced models like CN and RN to better utilize the textual features in a deeper and a more fine-grained fashion. And for the images and the videos, also I just, due to the time limitation, I just give a very brief introduction here. So for the image features, there is actually mostly used for fashion recommendation and recommendation of restaurants and hotels, because those will have a lot of images, and also could be used for the recommendations in image-related platforms like Flickr and Instagram. And also the nice thing about the image features is that you can actually besides those accuracy, but it also can improve the attractiveness of the recommended items. And for the video feature, and this is the area where we don't have much research, many papers in this direction. I think there's maybe two reasons. One is that the video features are very difficult and time-consuming to obtain. And also another reason could be that the videos actually contains just too much sensitive information. We found out that there's not many the public data actually has the has videos. And also the volume of the video features is generally very large, and so it will require huge computational power. So this could be possible reason why the deep learning models with the video features is actually quite lacking these days. But we were there when there's with this popularity of these short videos like TikTok and so on. And I believe that there will be more and more work on this in this direction, and we actually definitely need to study more in this area, along this direction. So also I actually along the talk I already gave you some of those open directions, and here there are some other future directions I want to point out. So how can we further improve the deep learning based recommendation with side information, especially in the complex structure? So for example, so this is the question we have to keep in mind, and perhaps we can consider those high level information in the intrinsic complexity of the structured side information. We can adapt those deep neural network to directly model the structured information. And another very challenging question is that oftentimes those side information that could contains a lot of noise, and how can we obtain high quality side information? Maybe perhaps we can rely on the crowdsourcing techniques. And another potential benefit of side information is that it could be utilized for cross-domain recommendation, because for cross-domain recommendation, right, you have a source domain and a target domain, and these domains have different differences and so on, but there could be, the side information could be common across these different domains, and then can build a bridge between these different domains. Another possible direction is utilize side information for package recommendation. So for package, you basically have a package of items, and then maybe these items can share some common side information like categories. So this side information can be utilized. So these are the possible directions. So here, because of the time limit, I only give you a very brief overview of this domain. And but if you want to know the details, you can get our survey paper, which is this published last year. And also, I want to take this opportunity to share with you a very exciting news that RecSys 2023 will be held in Singapore. This is actually after 10, since 10 years ago. It was last held in Hong Kong. So now after 10 years, it comes back to Asia Pacific. So it's actually quite exciting for us. So you're more than welcome to submit the papers and also participate to attend the conference in 2023. Okay, so that's all I want to share with you. And so if you have any questions.